Hi everyone, welcome again to Ventilator Engineering. Today's video is going to be a bit different from the last two in the sense that we're going to be looking at existing designs that are out there in the open source critical care ventilator community. Now, I'm not going to spend too much time looking into any individual design, but I do want to give people the sense for how to orient yourselves when presented with a new design and how to pick out details that may benefit you with your own projects. So for today, we're going to be looking at three projects in particular. And these are the Mechanical Ventilator Milano project, or MVM, the Operation Air project run by TU Delft, and the Vent for Us project, which is run through a Stanford, Utah collaboration. So I hope you can capitalize on all of the awesome open source materials that are out there for your own work and improve upon all of our stuff too. I've chosen these projects in particular because they're sort of more developed projects, and also because I've personally spoken to a lot of the people working on these projects, and perhaps I can share some of the insights that I have from being able to talk to these folks. So before we do that, I just wanted to make a quick note about medical fittings. I don't think it's worth dedicating an entire video to tech speccing for some of these smaller components like fittings, but I have noticed that people are asking about how they can figure out exactly which medical fittings that they need to connect their device to the gas supply at the wall of the hospital. So I think it's worth noting that medical fittings conform to NIST standards. That means that they're non-interchangeable screw threads. And what this means is that if I have O2 inlets and I want to connect to the oxygen at the wall, I don't want to accidentally be able to screw into the medical air fitting accidentally, so the screw threads are a bit different across the different gas supplies. And so sort of like if any of you have any types of flammable liquid containers at home, like propane tanks, you may notice that these tanks are reverse threaded, so you won't accidentally connect to them when you mean to connect to something else and cause an explosion. So it's sort of the same type of concept there. So when you're speccing these wall fittings, you need to look for not only the male or female form of the fittings, but also spec for the specific type of gas supply that you're working with. And downstream from there within your device, you can find adapters that connect to more normal fittings downstream, like NPT fittings, which are more common for general piping applications. So I just wanted to share with you before we move on some handy links here. And all of the links that I mentioned in this talk are down in the description below. But the ICU doctor we're working with specifically sent us this air oxygen blender as a representative gas blender that he uses at his hospital after we asked which specific types of fittings that we should be speccing for. And so this is a representative gas blender, and if you scroll down to the fittings associated with this gas blender, we have listed the input fittings to the device, and you'll notice that these are oxygen dis-female fittings of the female variety and air dis fittings of the male variety. And it also points out that these are NIST standards, right? At the output of the device, we have oxygen dis fittings of the male variety. So whenever we're looking for these parts, we need to be mindful of the gas source, right? So if I then go to wherever I'm trying to buy my fittings from, when doing part sourcing, for example, Precision Medical is one. If I scroll down to what they've got in their catalog, everything's sort of categorized by what type of fitting we're looking for. So there are Omeda-style fittings, DIS-style fittings, Schrader-style fittings, and so on. And regardless of what type of fitting categorization we're working with, they're always going to have different types of fittings based on the gas supply. So this is the sort of thing you're looking for. There are oxygen fittings, air fittings, and also vacuum, nitrous oxide, and so on. So keep that in mind. If you need connectors for your device, try to spec something normal downstream, and you'll have no problems just flexibly interchanging the medical fitting at the wall as necessary. Okay, So moving on to the design portion of our talk. As always, I have to bring up the simplified block diagram. I won't go into it in any detail, but I think it will help orient us as we encounter new designs to understand where we're working within this circuit, right? So for any given design, we'll be able to immediately try to identify the wall O2 and medical air inputs, or maybe the inputs from the external side of a gas blender. We'll be able to follow the inspiratory limb to the patient side at the endotracheal tube, assuming the patient's been intubated, and then follow the expiratory limb to find whatever flow controller components you have working down here. So that's what we'll keep in mind as we look through these designs. And the first one we're going to check out is the MVM, the Mechanical Ventilator Milano project. I've had the good fortune of being able to talk to Professor Gabbiati of this project and understand what their challenges were when moving through this design. So here's their website. You can find it in the links below. Since this is predominantly a group of academics, they're open sourcing all of their material through archive. So this is how people casually put papers out before they're peer reviewed. And when we open this link, the first thing that we're going to notice is that there are a ton of people working on this project. When I started following the project, there were around 40 group members, and now I think it's expanded even more than that. And what Professor Gabbiati has noted to us is that they had the benefit of collaborating very early on with manufacturing partners. So this has enabled them to gain access to a lot of the parts that other groups, for example, those groups in the US, have been unable to source. So that's a good tip if you're trying to get a head start in this type of crisis space. Okay, so you can read the paper at your leisure to find all of the details that are relevant to this project. We're only focusing on the mechanical schematic, but there's additionally a rough electrical schematic. There's information about their existing GUI, testing protocols, and so on. So feel free to read through all of this stuff. It's all open to the public. But for now, we're just looking at this mechanical schematic. Okay, so let's try to orient ourselves before doing anything else. So here on the left, we can immediately try to spot the air and O2 inputs to the system. Okay, downstream from there, we have this gray block, and at the outlet of this, we have a single gas supply. So it's pretty clear to us just by looking at this that this is probably some sort of gas blending system supported by the fact that the acronym is GB. And if you want to understand what all the acronyms are in this paper, you can go down and reference them below. But for now, we'll just keep tracing this route. So there's an additional line that runs to the patient down here. So here's the inspiratory limb of the device. And that means that this is probably the expiratory limb, which indeed ends in a PEEP valve. Okay, so we've sort of oriented ourselves to the general respiratory circuit that we expect to see. So from there, we can do more of a fine-grained analysis of this device. So following along the inspiratory limb from the gas blender, we have this valve-like symbol called PV1. So I may immediately assume that PV1 stands for proportional valve 1. And indeed, if you read the paper, this is actually a proportional valve, but my intuition about the acronym may be thrown off by PV2, which I don't believe is actually a proportional valve. I think it's more of a solenoid or process type, a solenoid valve. However, I do notice that this has the indication that it is NC, normally closed. So in the event of a mechanical failure, this valve is going to fail closed, which is probably good because it's, the gas supply is coming right into here. Whereas this one at the expiratory end is normally open, NO, which is probably a good safety procedure if, we have some other mechanisms built in to enable the patient to continue breathing, even if, assuming that they're able to breathe on their own to some extent. So good to note. Downstream from here, we have SB1, and this is going to be a spirometer, like the flow meters we've been talking about in some of the previous videos. So my first question is, which flow sensor have they been able to source given the resources that they have, and can I use that in any way? Because there are major supply chain limitations right now related to flow sensors. Downstream from here, we have the line to the patient. It looks like we have a bunch of pressure takeoffs here, as well as at various other places within the device. And I know from talking directly to Professor Galbiati that this is actually not the most recent version of their schematic. Here it's dated April 10th. It's currently May 2nd. But from their more recent schematic, I know that this group is working under the assumption that there will be an HME present at the proximal side of this respiratory circuit. So at the mouth, they're going to have a heat and moisture exchanger, which provides the heated humidification required for intubation of a patient, rather than something like a heated humidifier. Okay, and moving downstream, we have something that's probably a water trap, and then the expiratory valve, followed by the PEEP valve, where the expiratory valve has some sort of pressure assist. And we can look into the paper to see exactly what's happening there, and I'll get to that in a second. But let's look at some of these bits we've missed on the high pressure side. So here, after the proportional valve, we have a takeoff with an oxygen sensor. It makes sense to put that on the inspiratory side because they're probably just trying to get a digital readout of this gas blender. Some more pressure takeoffs. And then we have these two safety components right here. So the first one among these is an APL valve. So this is an anesthesia equipment specific part. And effectively what it is an adjustable pressure release valve. Pressure release valve, relief valve, and safety valve are all terminology for the same sort of thing. And this one has a little turnable knob that enables you to adjust that pressure level from 20 to 80 centimeters H2O. So for my purposes, I would try not to use an APL valve because I'm trying to avoid medical specific equipment. And I did ask Professor Galbiati about this device, and I asked if we could replace this with something like a fixed pressure release valve, and he said, yeah, you can totally do that, it's fine. So that's probably something I would shoot for in lieu of the APL valve. Likewise, additional safety components include this negative pressure release valve, and this is just a check valve that's facing inward. So if we think about how these valves are going to fail, if there were some type of mechanical failure, this valve would be normally open, and this check valve would enable the patient to take in air from the environment because it would enable flow to move in this way so that the patient can keep breathing if they're able to breathe on their own. So this is a good safety component, and we can continue tracing the other lines in such a way. The thing that I really wanted to point out is this sort of pressure assist on whatever type of valve they have going on here. And I don't want to dig into the details of this design too much because I know that their schematic is sort of rapidly changing, but I wanted to try to explain why you may need some sort of pressure assist on whatever expiratory valve you have at that end. So first I wanted to show you what a commercial PEEP valve looks like. So you may have seen these in some of the pictures of other folks' designs. And we have an adjustable setting that enables us to modify the PEEP value according to the linear spring constant of the spring that's in here. This is a standard commercial PEEP valve. You can look at the patent online, but more informative to our current discussion will be this fixed PEEP valve that I have here. So this is like a cheapo valve that comes with some existing respiratory circuits that you may be able to buy online. And it's fixed to have a single PEEP value at around 5 cm H2O. Okay, so I'm not going to be able to get the fine tuning that I want if I want to set my PEEP value to something like 15 cmH2O, but it's a good cheap component, right? So if I take this cap off, it has a port to the ambient. I sort of see how this device is going to work. So here I have air inlet from the expiratory limb on our diagram that's over here towards my PEEP valve. So the air inlet from the primary expiratory flow goes here. And then I have this line coming from the pressure regulator over here onto the top of the device. But let's take this cap off. If I can get it off. May not be able to get it off. There we go. Taking this cap off for a second. So without worrying about the airflow from the pressure regulator, this is the device that we have. So there's the air in from the expiratory end. And then there's this little tiny blue diaphragm at the top. And when your pressure exceeds the PEEP value of 5 cmH2O, this little diaphragm is able to lift off and release additional air to ambient, right? So that's how you get your pressure relief to the PEEP value that you desire. However, if you have this cap with the vacuum tubing from your pressure regulator, then assuming this device is connected, when you have airflow from the pressure regulator and airflow from the expiratory end, this diaphragm will effectively be in equilibrium and the valve will not release pressure to ambient, right? So you'll be able to control this type of diaphragm system by using a pressure regulator and maybe something like a solenoid to modulate this PEEP valve. So it's a pretty simple way to maintain your PEEP level if that's what you're shooting for. So when you see these sort of takeoffs from the high pressure side, that may be something that they're targeting. Okay, so to wrap up the MVM discussion, I wanted to put this in the context of my own design, because for my application, I'm trying to avoid a lot of these medical specific devices. Although the Milano team may be able to work closely with manufacturing and assure that they'll be able to source things like PEEP valves and APL valves and maybe fancy flow sensors, I may not be able to do that. But let's take a look at which flow sensor specifically they're sourcing here. So actually in the next figure, if you zoom in pretty closely, they actually do provide their bill of materials, where they tell you specifically what all of the individual components of their device will be. And if we zoom in even more, we can see some of these medical specific devices. Maybe this anesthesia associates part is the APL valve. They have some Honeywell parts. Komatsu might be something like one of the valves that they're using. But here I notice this Sensorion SFM 3300. So this is the flow sensor that they mentioned in this schematic. I think in their more recent schematic, they're using a different type of Sensorion flow sensor. But regardless, they're still relying on this commercial off-the-shelf flow sensor that we may not be able to find. So I may go and check out a few other designs to see if there are any workarounds that I may be able to benefit from to avoid using these parts. Okay, so let's see what the next design is that we want to consider. So we've looked at the MVM design. Now I want to check out the Operation Air design. Okay, so let's go to their website. I've put it in the link below. Here's Operation Air. So they have a very nice website with a lot of awesome publicity. Let's see if we can find their design. All of their open source materials available on this website, OSF. And here you can find information about their general design, hardware stuff, software stuff, and so on. We're just looking at the hardware for now. So this is where they're going to list all of their architecture, bill of materials, technical manuals, and so on. And the architecture is where I find this schematic. I'm actually going to look at it here in the slide so that we can zoom in on the next slide a little bit. Okay, so let's try to orient ourselves as we did before. I'll go a little more rapidly through this design. But here on the left, we have the air supply and the O2 supply. There are two parallel bits of this circuit that go through a NIS connector, some type of reducer, and ultimately an MFC, so a mass flow controller, on each limb of this. Then there's some mixing chamber. So here they're replacing all of the assumption of an existing gas blender with two mass flow controllers and a mixing chamber. Okay. So downstream from there, we're going to try to follow the inspiratory circuit to the patient. Here's where we're going to have the endotracheal tube and the respiratory circuit and everything else. And if we follow the expiratory limb, it looks like it goes down here and it vents to ambient air. Okay, so we'll just look at this very quickly. As I've said, we're making the mass flow controller assumption on each limb. We have some pressure takeoff, some safety components like the pressure release leaf valve to ambient. They have a high pressure side proportional valve, so this won't be as expensive as if we had a proportional valve on the low pressure side. And then we have a check valve to prevent air from moving backwards through the system, and the patient side over here. Walking through the expiratory limb, we go directly into an expiratory flow sensor. There's some other sensor takeoffs like pressure over here, some additional safety components like pressure relief valve and check valves. And then here we actually do have a low pressure side proportional valve. So if you'll recall from my video on speccing flow control components, we understand that the proportional valve that's spec'd for very high airflow and very low pressure is going to be way more expensive than something that works on the high pressure side with high airflow. So just from looking at the types of components that they're speccing for their device, we understand sort of what their project goals are. This isn't a super low cost device, but it probably is a rapid deploy device where they're trying to use as many off-the-shelf parts as possible. They're not relying on existing medical components like the gas blender. They're not relying on PEEP valves, so they're using this low pressure side proportional valve in lieu of that. And we can sort of get the sense for what they're trying to produce as a result of these components. Okay, and not to linger on this, we're just going to move quickly to the Stanford, Utah project, and this one's called Vent for Us. So we'll go to their website. And on their main website, they have some nice videos of the design in action. So you can try to look at those and get a sense for what the components are. But since this is another group of academics, they also post their stuff on medRxiv. It's a more medical device-specific version of arXiv. And again, here, this is how they open source everything that they have to offer to the community. They have information about their schematic, pictures of their testing setup, pictures of their wave outputs, and then, additional details about specific modifications that they've done to get away from using expensive components. But for now, let's just take a glimpse at their mechanical schematic and orient ourselves again. So here we have the gas supply, and it's just this single block. So they have this wall gas block that goes immediately into a pressure sensor. I'm assuming that this is the output from a gas blender. If we try to follow that to the patient, it looks like they have an HME, a heat and moisture exchanger, before the endotracheal tube of the patient. So it looks like this is the inspiratory limb to the patient. There's some sort of fixed orifice here. We'll have to think about what that means. And then the expiratory limb goes through some exhalation valve and exhalation control valve. So again, like in MVM, they have some takeoff from the high pressure side following a pressure regulator that provides some sort of control to the exhalation control valve. so we can read the paper in more detail to understand exactly what type of valves they're using here. They have a pressure regulator with an inhalation valve. This may be something like a proportional valve. They have safety components like the pressure release valve. That's all sort of standard stuff. But I noticed that they don't mention a flow sensor here. And the reason for that is made clear if you look at this fixed orifice and some of these pressure takeoffs. So effectively what they're doing, if you read this paper more carefully, is that they're using a tube with a known internal geometry that has takeoffs to a differential pressure sensor. And by using this differential pressure reading, in addition to understanding the internal geometry of this device, they can calculate the flow through this orifice without needing a commercial off-the-shelf flow sensor. So I actually really like this solution. I believe that this is the off-the-shelf fixed orifice that they're using. It's like an old school flow sensor that just has, the fixed geometry, some takeoffs, and here is where you would put the differential pressure sensor. So if we go to their paper and look at some of the pictures of their device, you can actually notice that differential pressure sensor here in the device internals. And here are the pressure takeoffs from that orifice. So that's a pretty nice solution. We'll probably test that with our system as well. And the other thing that I wanted to note about this device is that this is actually not a proportional valve if you go in and read the paper, because they are trying to get away with using lower cost components. What they're actually doing here is using a clamping system with a linear actuator to clamp soft tubing and achieve essentially the same effect that you would get from using something like a proportional valve to regulate pressure. So they call this the proportional pinch valve. And this is a pretty neat solution. You'll notice that they have to build this entire housing system for this pinch valve system. This is something that our team considered doing as well. They do have response time tests and repeatability tests. However, if I were going to use this type of system for my device, I would want much more extensive repeatability tests. Part of the reason we didn't go with this type of device was because we weren't sure if we could reliably characterize this for different temperature conditions, for different fatigue, modifications of the tubing, in the event that it became more brittle over time. And so I would really want to empirically test this sort of device for my own system very extensively before relying upon something like that. But it's really cool that people are starting to think about these workarounds for expensive components like proportional valves, because this is really what a low-cost design is going to rely upon. So that's pretty cool. So anyway, just to wrap up, we looked at a few designs very briefly. I hope you guys take the opportunity to look into all of these designs out there in more detail. And I wanted to close by giving you a link to our code. When you look at a lot of these designs that are out there, you notice that they share a lot of information about their mechanical schematics and electrical schematics, but teams, I think, have been lagging a little bit in sharing their code very openly and making their code understandable to new users in a way that it can be recycled. So in the interest of sort of strengthening the community, I invite anyone to go and look at our code. It's still very much a work in progress, but if there's any parts of this that you can steal from, please do that. And with that, I'll leave you for the night. See you next time.